So at this point, looking at our voxel of interest, again, ijk underlay to be 2672.4, let's also open up another AFNI controller, and we can look at the anatomical underlay here, and we can put the statistics on top of the anatomy. So in the lower left corner, let's click on the black new button, and we'll open up a new controller. And what you might notice there is in the upper left hand corner we have a B. So look at the windows along the top of the screen. You'll notice controller A, controller A, controller A in left in square brackets along the top. And in controller B window, we can set our underlay as it is. We can leave it to be the anatomy, and then open an image window there. And we can show we can even open a couple image windows, since we'll just look at the statistics here. We don't need there's no time series. I'm going to make these a little bit smaller just for saving screen space. So now let's start looking at the output of the 3D deconvolve command, the linear regression. So the first thing that we might actually do here is what does the linear regression do? It tries to fit the model to the data. So at each voxel, it's going to have a set of beta weights that are multiplied by each of the regressors in our X matrix here, so that the sum of them fits the data as well as possible. So, for example, at the current voxel, we might have 100 or so times, actually much more than 100. This is not scaled. I don't know, like 1200. What's the average voxel value here? The average here is 1285 or so. 1285 you see for the mean if you right click on the graph window. So anyway, so this will be about 1100 or 1200, say. And then plus some linear component from run 1. And then run 2, you'll have something close to the mean for the constant term, and then same for the run 3. And then you'll add some beta times the regressor of interest number 1, and then some beta times the other regressor of interest, and then different beta weights times all their motion parameters. And then if you add that all up, you get something that is close to the data here. So let's see what it actually produced for that. How well did it fit our time series at this voxel? To do this, we can do a double plot. Which is to say we can plot more than one time series in this window. The double plot should match the range, the display range for the underlay though. So if you double plot something that isn't in this 1100 to 1500 range, you might not even see it. To do the double plot, go to the opt menu here in the lower right hand corner, and we're not scaling our matrix, but you can look down below to the tran 1D. That's the 1D is like the time dimension, and that's currently set to none. Let's change that to be dataset number n. We're kind of going off the bottom here, so I'm just for opening the menu purposes, I'm going to squeeze this up a little bit. So opt tran 1D, and I'll change none to be dataset number n. And I'll click on that, and I get that plugin. Opt, change tran 1D, and now it's dataset number n. I'm going to cancel this just to close this menu. Don't hit done here. Done will actually close the window. You just want to cancel that stuff. So now I can make this a little bigger again. Beautiful. So now let's, for the extra time series we want to plot, let's choose the fit. So toggle input number 1 on, and then we can choose dataset, and we'll choose the second one shown there, rall_ fit time series plus orig. So that's again, this is 3D deconvolve fitting the model components, all these components, 6 polar terms, 2 regressors of interest, and 6 more motion terms. That's at at each voxel independently, it adds up some multiple of these 14 regressors to get close to the data. And let's see how it did. Let's change the color from red to dark blue. I kind of like dark blue. It seems to look better. And set and close. And lo and behold, now we have the fit time series in here. And you can see, if I make that fairly giant for the moment, just so we can see pretty well what happens, you can see how good a job it is doing, how close it's fitting the data. So this is actually fantastic. You'll notice that the fit time series is jagged too. It's an ideal, right? To some degree, shouldn't it be smooth everywhere? Well, not exactly. Remember, the blue is just a sum of these 14 terms. Sum, S-O-M-E, sum, S-U-M, of these 14 terms leads to that. And the motion parameters in particular are not smooth, and so any jaggedness that you see here is probably due to the motion. Everything else is smooth. So some of the motion is being used to fit this data. Anyway, fantastic. So you can actually see how big the beta weight is basically when compared with the data. Okay, so I'm going to make this a little bit smaller, and now let's go exploring the actual beta weights and statistics in the other controller. So we'll hop down to controller B, and I'll even open all three windows there, but I'll make it a little shorter because I want to see the other windows. And I'll set the overlay now to be the statistical output. That's what it's actually selecting by default here. Oh, it's not. rall_func. So this is that bucket output. If we look at our 3D deconvolve command here in the rl regress script, the bucket data set is called rall_func, and the +orig will be tacked on automatically. So that's the data set that has all the beta weights and stuff. If we run 3dinfo-verb on rall_func +orig, we can see what it contains. Now the history is tcat volreg and finally 3D deconvolve. And here are the contents. At subreg 0 we have a full fstat, visual reliable coefficient, and tstat. So the coefficient is the beta weight, the tstat is the tstat. We don't have fstats here because we didn't ask for them. The #0 is in the case where your basis function has multiple parameters. For example, if you use SPMG3, there will be 3 of them. If you use 10 functions modeled with 7/10, you'll have 7/10 functions, #0 through #6, etc. And then we have our GLT, essentially the beta weight, the contrast, the difference in beta weights in this case, and the corresponding significance. So, and we'll see that in the controller here now that we've chosen rl_func as our overlay. It opens up the define overlay panel. Again, these panels are just toggle. These buttons are toggles for the extra panels. We can see the overlay statistics here on top of the anatomy, because that might be helpful. And now let's start discussing the actual values in the data set and the colors or lack of colors that we may see everywhere. So we're at our voxel of interest. Let's threshold the data a little bit and colorize it. And let's look at something interesting. So I'm going to actually change this from the visual reliable result to be the contrast, V minus A. So we can set our OLA volume to be the V minus A beta weight, the coefficient, and the threshold volume. So this is the volume that we're using for coloring will be the beta weight, and the volume that we're using to decide whether or not to color at all, the threshold, will be our t-stat. And again, another way you can choose these things, if you have like more than 7 volumes, if you've got 200 for some reason, you can go to the text to the left of that chooser, the menu chooser, and you can right click there. So if I right click on OLA, I get a menu that is actually scrollable if it were tall enough, if I had enough volumes here, and then we could select the volumes like this too. So we could select 5 here. Anyway, so now we have colorization by the coefficient and threshold by the t-stat. So now let's threshold this a little bit, just so we don't see a full volume of color. We can threshold. We can start dragging this up. If we drag this all the way to the top, it goes up to basically 10. That's because the scaling on this is from 0 to 10 to the first. Zero's at the bottom here, and then up to 10 to the first. And you can change the scaling on that. Now it only goes up to 10 to the 0, but this is a t-stat, not a correlation. 10 to the 0 is probably too small, and 10 to the squared might be too big for a t-stat. So let's go back to 10 to the first, and we'll have it go up to 10. So if you don't know where to threshold, when you're just looking at data and playing around a little bit and just trying to see what is in the results, a common way to threshold, just to get started, is to basically raise the threshold until most of the speckles outside the brain disappear, whatever that happens to be. Or you can set a p-value. Let's do that alternative. So if we come up to THR here, I can right click, and now we can specify a p-value, a q-value. So we can type one in if you wanted to type in a p-value of 0.000162, whatever, and set. Or you can just be quick, and there's a separate command to just set p equal 0.001, and there you have it. So this is fine. We'll use p equals 0.001 for this example then. That happens to come out to a t-statistic of 3.3. So this is a two-sided test that we're thresholding by. We're thresholding both positives and negatives, and with p equals 0.001, and if you come up to the data set, we've got 436 degrees of freedom. Actually, this is our test, so I should look here, but they're all the same in this case. 436 degrees of freedom because there were 450 time points, and there were, then you subtract your regressors of interest. We have 6 and 2 and 6, so you subtract 14 from that, and you're left with your final degrees of freedom. And we didn't censor here, so we're not going to lose anything for censoring. So that p-value of 0.001 therefore will be converted to a t of 3.13. So now a lot of the voxels have lost their color. So let's verify now what colors they do get and why. First of all, at our current voxel, you see we've got 3 volumes here. We've got an underlay volume, an overlay volume used for color, and a threshold volume used to turn on and off color, or to allow or disallow color at each voxel. And at our current voxel, these are the values at that voxel. The underlay grayscale is 114, the overlay is 20, so that's the contrast between visual and audio is 20, and our threshold value is 5.29, so that's our t-statistic. Since at this voxel 5.29 is greater than 3.3, we see color here. And let me blow up a window just so we can look at it a little more closely. I'm going to just come over to the I guess I will use the coronal image, and I'll just crop it a bit. So I'm going to click on crop, and I'll just make a little rectangle somewhere near where we are. And now we won't see so many voxels, but we'll be more sure about which voxel we're looking at. And if you wanted to, like if these crosshairs are not clear because you can't see them well enough for some reason, you can change the color. If I come over here, I can change my crosshair color from green to dark blue, which may not be a great choice in this case, or whatever. But just so you know, you can change it. I'll go back and leave it as green. And there's this, in the image window, there's this C button here. You can kind of close the crosshairs to be very positive of which voxel you're looking at. One other small thing to note here is that there's a difference between the resolution of the underlay dataset and the resolution of the overlay dataset. So there may actually be an interpolation effect. If you click, first of all, if you click on Define Data Mode here, that toggles a different window pane. The Overlay Resample mode, supposing that the underlay and overlay have different grids, is nearest neighbor, NN. There's linear, cubic, and this block mode that I won't talk about here. So if you wanted a smoother outline, you could change these things to cubic, and now you get this smoother outline. But that's not real in terms of our data, so I'm going to go back to nearest neighbor. But just so you understand, the colored voxels here are so much blockier because it's at a lower resolution. If you recall, the resolution of the underlay voxels is basically 2.75. That's the overlay. The RL func is 2.75 squared by 3 millimeters. 3D info on anat+orig shows basically almost 1 millimeter isotropic. So much higher resolution. So now let's think about what colors we're seeing. So I'll close this panel and leave the Define Overlay panel open. And so we've decided we're thresholding at 3.3 for the T statistics, and we know that, so at the current voxel it's 5.29, so we see color. If we go outside that location, the threshold at this voxel is now 2.1. That's less than 3.3, so it's not colored, and that goes plus or minus because this is a two-sided test. The current voxel is negative 0.1, basically 0.09. Again, that's too small in magnitude, so it's uncolored, but if I click on the blue one, that's negative 3.43, greater than 3.31, and so we do see color. So this is all done by the threshold slider bar and the threshold volume. And then you have to ponder the current voxel's value as to whether or not you see color. So now we know when we do see color. Let's now decide what color we should see. So the coloring is done by the OLE volume. In this case, it's the V minus A, the contrast, visual reliable minus auditory reliable, and then applied with this color scale. So the color scale you see currently goes from like negative 7.6 to positive 7.6. And that's due to this auto range button being toggled on. It's usually on by default, unless you turn it off, or unless you're looking at an ROI dataset. But the auto range is going to come from the OLE dataset, and then maybe a I think like a 90 percentile for it, something like that. Just to come up with some range that you might see some variance in the colors. In this case, we don't. It's not very good. Um, Remember, the average here is about 1200 in our time series. The mean is 1257 if I right click on the graph window. So a 1% signal change is like 12 and a half. So 7.6 is kind of small. With this with these strong responses, we're comparing visual and audio stimuli against fixation. So we see very strong responses over a 20-second stimulus. So this is kind of small. So let's bump this up to maybe, I don't know, 20 just to see. So if I type in 20 here, now you see the scaling goes from negative 20 to 20 with 0 being in the middle. This is the, if I right click on the color bar, you see, if you can choose the color scale in our current reds and blues inverse, which you probably can't read here. I can barely read it. Is this reds on top and blues on the bottom with 0 in the middle, just so there's a clear distinction between what's positive and negative. So now at our current voxel, we have this light blue color, and that's because the contrast value, the V-A coefficient, is negative 5.4. So where does negative 5.4 fall on the color scale? 0, negative 20, it should be about a quarter of the way down. And, whoops, if I right click on here, the value it shows, here is negative 5.56. So right about here is where this voxel's value hits the color bar, and so it gets this color. And over back at our red voxel, the value is again 20 there. It's basically pegged at red. And if we see there's some orange voxels here, I'm just clicking around in the axis image now. This orange voxel, we have a contrast of 6.2, so that's maybe a third of the way up here. So a little higher than this. So right in here, this orangish color. So that's how the voxels are colored. Now let's jump back to our voxel of interest. So I'm going to right click again and jump to ijk. But now we have to pay attention. Do I jump to ijk-UL or OL? If we jump to ijk-UL and type in 2672.4, so I'm doing the I'm having mouse troubles here. If I jump to ijk-UL, that's the underlay, and type in the same values as before, lo and behold, we're out in the middle of nowhere. What in the world happened? Well, again, our underlay data set, the grid is 256 squared by 175, and this 2672.4 are indices into the matrix. I clicked on jump to ijk for the underlay, and so it's using the underlay grid 0 to 256, 0 to 255, 0 to 255, 0 to 174, and so this is going to end up way off to the side. As opposed to if I scroll up, we have our overlay data set. The EPI resolution is 0 to 79, 0 to 79, 0 to 32. That's what this applies to. So in this case, we actually want to, I'm going to right click and jump to ijk for the overlay resolution. Of course, we could have done this in controller A because we're looking at the EPI data in controller A, but this is a good excuse to see the distinction. So let's jump to 2672.4 here for the overlay resolution. And that's back where we want to be. So now what do we actually see at this voxel? We see a contrast value of 20. Where does the 20 come from? Well, it's this contrast is V minus A, and the contrasts are a single line contrast is just some linear sum of the beta weights that it applies to. In this case, it's the visual beta weight minus the auditory beta weight. And you can check that if I set my OLE volume temporarily to be the visual reliable beta weight, that's 123. If I change it to be the audio reliable, that's 103. And their difference is, if I get out my calculator, 123 minus 103 happens to be 20. So that's why we see the contrast. So it might be more interesting if we see, so at this voxel we're seeing a fairly large contrast. That means the visual reliable beta weight ought to be large. But let's cheat and let's find some better places where the contrast is even more clear here. So I'm going to leap up to the clustering menu now. Let's clusterize this, and let's look for clusters where the V minus A t statistic, we have large clusters of contiguous voxels that are super threshold. So let's clusterize. I'll just run through this very quickly. In the clusterize menu, you can choose the nearest neighbor level, the number of voxels that are required for the cluster, and the cluster type. The nearest neighbor 1, 2, and 3 is just faces are touching. So if you have a central voxel, a central shoebox, it has 6 faces. So there are 6 first neighbors. And then if you allow the edges to touch, picture a 3 by 3 by 3 collection of shoeboxes. There's a central shoebox, a central voxel, and then there are 6 first neighbors around it. If the faces or edges can touch, there will be 18 second neighbors. And then if you allow the 8 corners of that large 3 by 3 by 3 collection of voxels, if you allow the 8 corners to be connecting, then you'll get 8 more voxels in there. So you'll get 6 or 18 or 26 neighbors in these 3 cases. And of course there's one central voxel, which would give you 27 in that 3 by 3 by 3 grid. So that's the NN level. And then the voxels is, of course, the minimum number of voxels within a cluster that are considered enough to be significant or whatever you're significant, or just something that you're playing with. And then the clustering type can be bisided or not. The positive or negative or two-sided will be determined by the GUI. If I right click on this threshold again, you can do positive and negative, positive only or negative only. So that can give you a one-sided or two-sided test. But even given that you're doing one-sided test, you may want bisided clustering or not. Bisided is probably the most natural way to cluster, though it's a fairly new style of clustering, at least to formally define it. Bisided clustering is where you can have a cluster of positive voxels and a cluster of negative voxels, and they don't count for the cluster sizes between each other. So if we require in our clusters to have 40 voxels, in the case of bisided, if it's a positive cluster, it's got to have 40 positive voxels in the cluster to survive, or 40 negative voxels. If bisided is off, it could have 30 positive and 12 negative, and it would still be big enough. So we don't want positives and negatives to be part of the same cluster. We want them to be separate clusters. So fantastic. Enough babbling about that. Let's just hit set. We can just keep these defaults as they are. I don't know if I changed that too. So now let me turn it on and off that a little bit just so you can see it in the GUI. If I clear it, watch what appears in the 3 windows here. clear the clustering, you've got all the little speckles of results all over the place. If I clusterize again and hit set, we can watch the image windows. All that stuff is gone. So that's the effect of clustering. So all those little speckles, they weren't part of, they weren't parts of 40 voxel clusters. So now let's hit the report button, RPT, under clusterize, and we can see what actual clusters exist. So given our thresholding, the GUI has made clusters throughout the volume, and here are the sizes of the clusters here. You notice the bottom one is 50. In the interface, basically, we specified a minimum of 40. All that does is tell AFNI where to cut off this list of clusters. If the bottom were 30, now the smallest cluster size here is 31. And all it does is say draws a line in this cluster table and omits the things that are too small. So let's see what clusters we found. Notice a little thing here. Our current, wherever the crosshair happens to be, we're part of cluster number 4. But let's take a look at the clusters here. If I jump to the first cluster, we get some negative cluster kind of in the middle, mid-sagittal area. If I make that flash, okay. Jump to the second cluster, we've got a visual cluster that seems to be only on the left side. The third one, what in the world of that is that? Well, what this is a nice demonstration on why we don't like to mask our results. So remember, so first of all, what are we seeing? Why are we seeing anything here? Or what can we imagine as to why? I'm not going to presume to know, but I'll just guess. So this is clearly outside the brain. What that likely is, maybe it's muscles along the temple area. We do things when we're concentrating on something, for example. When we may squint our eyes to focus on some image that we're seeing. So if the subjects are showing videos of people speaking words, they might squint a little bit to possibly feel like they're improving the vision, cutting out the excess light to maybe see a little more clearly. Or it could be, a slight clenching of the teeth or something like that. Either one of those could produce some sort of muscle movement, and if that happens in time with the stimuli, that's going to be something that our model is going to pick up. If it happens in this on and off pattern reasonably well, we're going to see that. And if you look at the time series, here's the current voxels time series. I'll make this a little bigger. It doesn't look so pretty, but you can see the bump here, bump here, bump here, bump here. It's noisy because this is not a nice smoothed bold signal. We haven't even smoothed these time series, or these volumes I should say. But you can see that it is going up and down in correspondence with the actual say stimuli, or even the stimulus response, the idealized responses. If I leap down to the FIM button, let's see if there's an ideal we can choose here. Maybe there isn't a great one, but let's just put run ones back up here, even though it doesn't cover the whole thing, so we can see how things might correspond. If I do plus here, make this taller. No, that didn't help. But anyway, you see these bumps here, and they don't have to perfectly match, but as long as this explains a lot of variance, then we might get, maybe get voxels that look like something's going on. So now, again, note that we haven't blurred this data. What happens if we blur this? Well, we may mask it or not with the blurring operation, but this could bleed into the brain fairly easily if you're not pretty precise on how the blurring works. And if this, say, let's assume this is a muscular, say, activation, say, if we blur this and it goes into the data set, then if the data's been masked, you may end up trying to explain this somehow with as a bold effect, even though it is not, and that's terrible. I mean, that's certainly not something you would end up wanting to try to put in a paper. You know, hopefully this would not match anything real going on. But if you don't mask the results, you can see, oh, this is something I may have to worry about. It may bleed into my results. I may have to explain it in the paper and say, this is just some muscular responses bleeding into the brain, but it's not an actual bold response. So you might have to explain that in a paper. And if you haven't masked the data, you might not realize that it is just a muscular response. Okay, so let's move on to the next cluster then. Cluster 4 is, say, the right visual area. Cluster 5 is, I don't know what that is. I'm not going to pretend to know all these things. And then you get some auditory area here. So let's just look at the auditory area. You note again that what we're coloring, we're looking for voxels with a large contrast. And if I go up to the fit time series here, what you notice is the first two bumps in blue there are actually, those are auditory reliable stimuli. And then we have, after the first two auditory reliable stimuli, you have three visual reliable stimuli. You can see in the X matrix here. So you notice that the audio responses are big, big, and then shorter, 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 and then a bigger response, and then a shorter response, and then a bigger, and then a shorter. You're seeing a voxel where the beta weight for the audio reliable condition is larger, or the response, than the beta weight for the visual reliable response. And so this current voxel has a large contrast value. The contrast is negative 48.6. So, you know, so that's the beta weight for the visual reliable is, let me close this. The beta weight for the visual reliable was 80, and the beta weight for the audio reliable is 128. So you subtract them, you get negative 48. And so, and it's significant because it explains a lot of variance. The t-stat is negative 9.2. So that's great. I think we can end the video there. That pretty much covers all of this. The basic thing we want to understand is the regression matrix and how it's our responsibility to create a useful regression matrix, and 3D deconvolve's responsibility, or Remofit's responsibility, to fit that those time series to the data as well as it can. And then the blue curve will be the fit, and the residuals will be the difference between them. And the residuals, like the beta weight with respect to the residuals, will give you some t-stats or f-stats or whatever. Or I guess not f-stats, but t will be that ratio. So I'll end it there. Thank you.